3.2.4 Phase change processes. Van der Waals gases. For diatomic in center of mass with spherical coordinates for a rotational part, have for energy. See equation 3-96. Initially there are only the x, y, z motions like monatomic, so 3 degrees of freedom. Then add the angular motions, are fixed, to have 5 active terms. Lastly, have full vibrational, thus 7 degrees of freedom. Interestingly, if we consider the plots of the pressure-volume curves for a gas at various temperatures, we have a clear physical property when the curves are flat for any stretch of volume, i.e., when partial derivative of P with respect to V equals 0 on a constant temperature curve for a region of volumes. The formalism is already indicating a gas-liquid biphase in this constant region, condensation occurring. The first such region encountered as curves with lower temperatures are considered will not only have partial derivative of P with respect to V equals 0, but also the fraction with numerator partial differential squared P and denominator partial differential V squared equals 0, and the constant region will be reduced to a point, known as the critical point. The temperature at the critical point then defines a clear separation in thermodynamic phases.
T is less than T sub C, always a biphase region, condensation. T is greater than T sub C, no biphase, no condensation. T equals T sub C times WH of E of RE of partial derivative of P with respect to V equals 0 times AND of the fraction with numerator partial differential squared P and denominator partial differential V squared equals 0. If T is much greater than T sub C and P is much less than P sub C, then have thermally perfect gas. T can increase until dissociation or ionization occurs. T sub C is much less than T is less than T sub D times OR times T sub I.
More detailed derivations of thermodynamic properties are given in reference 6, and we arrive at see equation 3-97. Example 3.4. The van der Waals equation of state is an analytic expression that captures in a general way some aspects of real gas effects and has historical significance. Given the van der Waals expression, see the next equation. Evaluate A and B in terms of P sub C times AND times T sub C by using the fact that this thermal equation of state must demonstrate the correct physical P, V, T behavior near the critical point.
Solution. Starting with P plus the fraction with numerator A and denominator V squared times V minus B equals RT, near the critical point. See the next equation. Evaluating. See the next equation. We have 2 equations and 2 unknowns. See the next equation. Solving we get. See the next equation. Thus, see the next equation. Since we need A and B in terms of P sub C and T sub C, evaluate at critical point. See the next equation. Now we have.
See the next equation. To get, see the next equation. Example 3.5. Expand the van der Waals equation as a virial expansion and evaluate B of T. Solution. The virial expansion goes as PV over RT equals 1 plus B of T over V plus O of V to the negative 2 power. Using the form of the van der Waals equation given above, see the next equation. We get, see the next equation, where PB divided by RT must be expanded by way of Taylor series with focus on terms of order 1 divided by V. The term negative A divided by RTV is explicitly of order 1 divided by V. Thus,
start with. See the next equation. Thus, we need to Taylor expand the fraction with numerator 1 and denominator V over B minus 1 and pick off the order 1 over V term. For V is less than B colon the fraction with numerator 1 and denominator V over B minus 1 implies negative 1 minus V over B plus V over B squared ... in which case there is no extra 1 over V term and B of T equals negative A over RT for V is less than 1/3 V sub C. Since B equals 1/3 V sub C, this case essentially corresponds to condensation, where the equation isn't as accurate. For V is greater than B colon B over V times the fraction with numerator 1 and denominator 1 minus B over V implies B over V times 1 minus B over V plus V B over V squared ... and we have an additional 1 over V term, thus
B of T equals B minus A over RT times F of O R times V is greater than 1/3 V sub C. 3.2.5 Isentropic change, adiabatic change, and Joule-Thomson expansion. Let's consider the perfect gas undergoing isentropic changes. Start with a perfect gas in variables exhibiting entropy. See equation 3-98. For thermally perfect gas, dE equals C sub V dt, P over T equals R over V. So, see equation 3-99, and we get see equation 3-100. Define is identical to the fraction with numerator C sub P and denominator C sub V. In general, gamma equals gamma of T is a monotonically decreasing function, and we have see equation 3-101.
Now, specify isentropic conditions. See equation 3-102. If gamma equals const, if calorically perfect, then see equation 3-103. Rho equals const times T raised to the fraction with numerator 1 and denominator gamma minus 1 power, and times using of P equals rho RT. Econ 3-104. See equation 3-105. Example 3.6. Consider compressing a gas isentropically from P sub 0 equals 0.05 MPa and V sub 0 equals 1 L to V sub 1 equals 0.1 L. So, how much work is done? What is the final P?
Solution. Recall. P sub 0 V sub 0 to the gamma th power equals P sub 1 V sub 1 to the gamma th power vector P sub 1 equals the fraction with numerator P sub 0 V sub 0 to the gamma th power and denominator V sub 0 to the gamma th power. The work done on the gas. See the next equation, where for air gamma equals 1.4. Thus, see the next equation.
And see the next equation. Now do same thing isothermally. See the next equation. Thus, see the next equation. So it is less to compress isothermally than isentropically. Example 3.7. Helium at 200 degrees Celsius enters a system at 2.0, standard, ATM. 1 ATM equals 0.1013 MPa, goes through a Joule-Thomson section dropping the pressure to 1.5 atm, and finally is expanded adiabatically to the environment, at 0.95 atm. What is the temperature change through this system? What is the specific entropy change?
If expanded isentropically, assume that we can consider helium a perfect gas, monatomic. T equals 200 degrees Celsius J, Tt, equals 200 degrees Celsius isentropic T equals P equals 2 atm P equals 1.5 atm P equals 0.95 atm. See the next equation. For a perfect gas PV equals nRT. See the next equation. Thus, partial derivative of T with respect to P sub H equals 0 during the Joule-Thomson section. During the isentropic expansion we use P sub 1 V sub 1 to the gamma th power equals P sub 0 V sub 0 to the gamma th power, or T sub 1 V sub 1 raised to the gamma minus 1 power equals T sub 0 V sub 0 raised to the gamma minus 1 power, where gamma equals 5/3. Thus, see the next equation.
And see the next equation. Consider the entropy change during Joule-Thomson expansion. See the next equation. For a perfect gas, thus, see the next equation. Since temperature remains constant in the JT expression, this simplifies to see the next equation. For the specific entropy change we have delta S over M equals delta S equals NR over MLN of the fraction with numerator P sub 0 and denominator P sub 1. Example 3.8. Two rigid containers, volumes V sub 1 times A and D times V sub 2 of a perfect diatomic gas, initially at pressures P sub 1 times A and D times P sub 2 and temperatures T sub 1 times A and D times T sub 2 are brought into thermal contact. Express the change in specific entropy of the entire system, i.e., both containers of gas, in terms of T equals the fraction with numerator T sub 2 and denominator T sub 1, P equals the fraction with numerator P sub 2 and denominator P sub 1, A and D times V equals the fraction with numerator V sub 2 and denominator V sub 1. This entropy change must be consistent with the second part of the second law. Show this for the special case that the masses of gas within the two containers are equal.
Solution. For a perfect gas U vector U of T. Since C sub v equals partial derivative of u with respect to tau sub v equals du over dt equals 5 halves nr for a perfect diatomic gas, we have u equals 5 halves nRT, also PV equals nRT. Consider TdS equals du plus PdV. See the next equation.
So, see the next equation. We're discussing the specific entropy, so this is. See the next equation. If the systems are brought into thermal contact, eventually T sub 1F equals T sub 2F equals T sub F comma V sub 1 times A and D times V sub 2 remain the same, and P sub 1 times A and D times P sub 2 change according to the final temperature. See the next equation.
Thus, see the next equation, and see the next equation. Now, from conservation of energy, 5 halves n sub 1 are T sub 1 plus 5 halves n sub 2 are T sub 2 equals 5 halves n sub 1 are T sub F plus 5 halves n sub 2 are T sub F. Thus, T sub F equals the fraction with numerator n sub 1 T sub 1 plus n sub 2 T sub 2, and denominator n sub 1 plus n sub 2 period.
Substituting this back. See the next equation. If the masses of gas are equal, n sub 1 equals n sub 2 equals n, and we get. See the next equation. The second part of the second law basically states that entropy is maximized during any reaction, thus the fraction with numerator partial differential delta S sub T and denominator partial differential T equals 0 if true. Let's find out. See the next equation. Together with PV minus T equals 0, we get the fraction with numerator partial differential delta S sub T and denominator partial differential T equals 0, and it checks.
Example 3.9. Recall that for blackbody radiation F equals negative PV and see the next equation. For an isentropic process, use the T-V behavior of this thermodynamic system to calculate an effective gamma for a photon gas in analogy to an isentropic perfect gas. Solution. See the next equation. ds equals partial derivative of s with respect to t sub v times dt plus partial derivative of s with respect to v sub t times dv, and using the Maxwell relations. See the next equation.
Since. See the next equation. We get. See the next equation. This corresponds to a perfect gas with 1 divided by 3 equals gamma minus 1 implies gamma equals 4 divided by 3.